Have you ever tried to take a photo of a TV or monitor and noticed a weird effect? Cameras are supposed to be able to capture the real world, but in real life, there aren't these black bars moving across the screen. So what's going on? Even if there's nothing wrong with your 3D data, you can still end up with artifacts in your 2D rendered image. Unlike data artifacts, which can look strange but can be intentional on the part of the scientist, image artifacts are generally due to a limitation of the technology and are a problem in a visualization. The effect you see when you try to take a picture of a TV screen is a type of image artifact called a moire pattern, which happens due to pattern interference. Both the camera and the display screen are using a scanning technique to capture and display images, and the scans of each device produce conflicting sets of lines. More generally, a moire pattern is a large-scale pattern that appears when you overlay smaller patterns, and that often happens on accident. It can occur in your visualization if you have two or more volumes or other semi-transparent objects with different noise patterns in front of one another. One of the most common ways you may see a moire pattern in your visualization is if you downsize your output images. Here's a full-resolution photograph. This roof is made up of very fine lines, some of which are just about a pixel across. If I shrink down the size of the photo, the pixels of the large image are selectively sampled down into a smaller image in a repeating pattern. Let's blow that back up to its original size to get a better look. Moire patterns are one specific type of aliasing, which refers to more general discretization artifacts that occur when something in an image should be continuous. Aliasing is a common problem with pixel-based raster graphics that boils down to the idea that you can't accurately represent diagonal lines on a computer. If you have a straight horizontal or vertical line, every position on the line is in one row or column of pixels, so there's no problem. But if you draw a straight line at an angle, because the computer has to convert it into a series of pixels, it ends up having jagged steps. There is an operation called anti-aliasing that you can apply, which fuzzes these steps so they're less apparent, especially when your pixels are small enough. There are many issues in computing around the fact that lines, pixels, numbers, and all continuous things have to be discretized into some finite representation. Color banding is an image artifact that occurs due to discretization of color, and it looks something like this. The reason this happens is that you can't portray a truly infinite variety of colors on a computer. You have to discretize them by representing the red, green, and blue values with some fixed number of bits. The more bits you use to represent your RGB values, the larger your color palette becomes. Color banding can be used intentionally, and in fact, it's a feature in standard photo editing software called posterization. People sometimes use it for artistic purposes, but it's more likely to come up as an artifact in terms of working on a scientific visualization. Here's the colliding galaxy image shown using a palette of only 4 colors. As we increase the number of colors available to us, the banding becomes less and less apparent. A larger color palette comes at the cost of a larger file size. Sometimes color banding can be the result of software trying to optimize the image to make the file size smaller. Decreasing the size of a file or a collection of files is called compression. There are many different compression algorithms. Some are lossy and some are lossless. Compression that results in color banding is a type of lossy compression, because you end up losing color information that was present in your original image. If these were the pixels of your original image, a lossy compression algorithm might combine colors that are similar to each other. A lossless compression algorithm, however, would combine only pixels where the colors are actually identical. This results in a smaller file size, but you don't actually lose any information as compared to your original image. Most video, sound, and image formats compress your file in some way. Here's an example of a video that's been uploaded to YouTube and compressed once.
I'm sitting in a room different from the one you are in now. I am recording the sound of my speaking voice, as well as the image of myself. And I am going to upload it to YouTube, rip it from YouTube, and upload it again and again, until the original characteristics of both my voice and my image are destroyed.
Here it is after it's been downloaded and re-uploaded 10 more times.
I am recording the sound of my speaking voice, as well as the image of myself. And I'm going to upload it to YouTube, rip it from YouTube, and upload it again and again.
Here it is on the 100th re-upload.
I'm recording the sound of my speaking voice, as well
and here it is on the 1000th re-upload. As far as common image formats go, JPEG and GIF images, for example, use lossy compression, but PNG and TIFF are lossless. This image is about 800 kilobytes saved as a JPEG, but 2,000 kilobytes, or 2 megabytes, as a PNG. It's 2.5 times bigger, but it doesn't have any color banding. In addition to trying a different file format, you can actually stop color banding by adding a bit of film grain to your image. This interrupts the compression algorithm because nearby pixels aren't necessarily going to be similar colors anymore with the added noise. Film grain is one type of noise that you can use intentionally, but noise is often an image artifact if it's not an intentional design choice. You can get a noisy 2D image due to low sampling of your renderer, or a spotty 3D scene due to low sampling of your light sources or volume sampling. These different sampling issues can end up looking similar, so you may want to check both your 2D and 3D settings if you're seeing unwanted noise in your rendered image. Image artifacts are more likely to be problems rather than features in a visualization. More often than not, aliasing, color banding, and noise can be minimized with a simple change of render settings, as long as you know how to recognize and identify the problem. Fun fact, moire patterns actually have some pretty cool real-life applications. They're used in marine navigation to point out hazards, making an arrow that points in a different direction depending on your angle of view. They're printed on banknotes so that when money is scanned, it creates a wave pattern, making it harder to create counterfeit bills. They're used in super-resolution microscopy, making it possible to get images that are higher resolution than would otherwise be possible. And they can be used to create some pretty fun motion effects.